Hello everyone, my name is Liu Khanh Nguyen, the first year PhD student in robotics at RSS. So today I will present my recent work on a sim-to-real learning technique for large-scale vision-based tactile sensor and a novel design of a sensing link for robot arms that features both proximity and tactile modalities based on the vision-based technique as the one that you can see here in a short video. Before we are going to that, I would like to make a brief introduction to the design of our large-scale tactile sensor called TAC-Link and its learning-based sensing methods. Basically, this sensor uses two opposite cameras inside the link to track the deflection of markers in the context, which can give us the global skin deformation. In this work of my colleague, he set up an experiment to collect training datasets to train a neural network that can reconstruct the skin shape in real time. The datasets includes pairs of tactile images and respective data of skin deformation at different indentation depths collected on the entire skin surface. And once training, the model could reconstruct 3D shape of the soft skin at high sampling rate of around 30 Hz. However, one of the limitations of this method is that we need to set up experimental systems, which is cumbersome and time-consuming process. And so to mitigate the need for collecting real experimental data, obtaining training dataset in simulation environment could be a promising solution. With this in mind, we propose a simulation platform that comprises physics engines SOFAR and Gazebo. As such, the neural network for the shape reconstructions can be trained by simulation datasets, which includes the skin deformation and virtual tactile images. So for collecting the data of skin deformation, we use the FEM-based SOFAR simulation tool to model the soft skin with accurate material properties using a calibrated mechanical model. And this visual model with embedding markers are utilized for virtual image rendering based on the Gazebo. As you can see here, the skin deformation can be represented at the nodal displacements of finite elements in the skin model and serve for the labels of the thickness model, which had the inputs of virtual tactile images. Here, it is possible to collect the datasets with different contact conditions. For example, the double bond contact, like the one that you can see here. Here, we evaluate the performance of the trained model on the shape reconstruction task. Not only evaluate the model on the simulation images, but we also verify the transferability of the model on the real ones. But unfortunately, the results show that the model could generalize well on the validated simulation images, but not the real data, which is about 0.7 and 5 millimeter of Bruce mean wear error, respectively. And here's a live demo on several test samples of simulation images. It can be seen that the skin shape reconstruction quite matches to the baseline data. And conversely, the samples of real tactile images captured from the physical sensing device result in bad inference of technique model. Hence, let's see what we can do to resolve this problem. The inaccuracy inference of the model on real visual inputs can be accounted for by mismatches between the simulation and real images. So to address the problem, here we propose an R2STN network that could translate the geometric perspective of real images into the virtual ones before they are fed to the technique model for shape reconstruction. And for this purpose, the R2STN model is trained in adversarial manner, where it plays a role as the generator of a GAN framework, which competes against a discriminator in order to achieve its best in the translation task. Indeed, with the intervention of the transformer network, the sim-to-real gaps on the reconstruction task could be reduced significantly, which attains a root mean wear error of around 1.6 millimeter for a real sample in the double contact scenarios. And clearly visualized in this live demo, by passing real visual inputs through the R2STN network, the performance of the shape reconstruction task on the real images was improved significantly. And here's a video showing the tactile sensing performed real-time on our large-scale tackling device using the sim-to-real technique that I have presented. As you can see, the sensor can feel the touch with diverse contact conditions, such as the double and even triple contact points. And with the help of GPU computing, the sampling rate can attain up to 100 Hz. Now I would like to briefly introduce to you our recent development of a two-mode vision-based proximity and tactile sensing link for a robot arm. So the main idea is to integrate an additional proximity modality into the current tackling device without any further hardware edit. So to realize this, we need to address the question is that, can the surface sensor skin actively switch the skin transparency from the dark state to the transparent state so that the two cameras inside the link could see through the skin for estimating the distances of objects that are close to the skin surface. And when the skin returns to its original dark state, the same sensing methods that I have shared with you for tackling device could be applied for tactile perception. Here on the right-hand side is the camera view of the transparent skin, and its constructed depth map utilized for distance estimation. And on the left-hand side is the skin being in the dark state, which is suitable for the tactile sensing mode. Now let's see the design of the two-mode sensor named as Protect. The overall design of the sensing link is fairly similar to the tackling device. However, the main difference lies in the construction of the surface sensor skin. The transparency switch can be realized by a two-layer skin structure, which includes an outer surface transparent layer and an inner PDLC film. So what is the function of the PDLC film? As you can see in the left-hand side video, by applying an electrical voltage, the PDLC film switches the state from the opaque to the transparent so that the external environment can be seen from the inside, which enables the proximity mode. Moreover, it can also return to its original dark state, which definitely expected behavior for tactile perception. And this is the construction of a robot arm, which includes two Protect links, which are connected through an electrical motors. Now I would like to share with you some demonstration of the Protect arm's behavior that reacts to the close object distance observed in the proximity mode. And in the left-hand side video, we apply for the robot a simple reflex behavior based on an admittance control framework. And on the right-hand side, the robot can slow down the speed as the close distance is observed between the human and the Protect link. And here the video shows the reflex behavior of the robots based on the force signal provided by the Protect link, as in the tactile sensing mode. And so to summary, in this very first demo, it can be seen that without any additional hardware, we have been able to integrate both proximity and tactile modalities into a single robot link. And that's the end of my presentation today. Thank you very much for your listening.
So we'll save the question for the end. Thank you, Christina. I think you're early on there. So moving on, our next speaker is DGR-POMDP. That's it. I pronounced your name wrong.
Yes, I'm here. I'm just fixing.
All right, wonderful. So you first going to tell us about improving inference of human plan by modeling language feedback, coming from Brown University. Please.
Thank you. Hello, everyone. My name is Ifra Idris. I am a fourth-year PhD candidate at Brown University, and today I'll be presenting my work on improving inference of human plan by modeling language feedback. This is a joint work with George Konadaris and Stephanie Telex. So the problem that we are trying to solve is that we want the robot to be in close proximity of the humans and where the robot can actually interact and plan while the humans are completing multiple hierarchical tasks, such as the human is cooking or is performing as an exercise. or is operating the machines. In order to do so, the robot actually needs to be able to understand the goal that the human is trying to do while getting information only through the world sensors. Further, in case of a conversational social robot, which actually asks clarification questions in case it's confused what the human is trying to do, and it gets a language feedback from humans, it needs to be able to also incorporate the language information that it is able to get. So now a lot of work has been done where they're trying to enable the robot to do goal recognition of humans. Now, these works, they can be largely categorized into these three types. The first is the context aware social robotics, where they work a lot on grounding the language in terms of the environmental context. But the speech that is generated from the robot, that is mostly heuristic and is not grounded in the environment context or the user modeling or the dialogue context, all of it together. Then another type is the dialogue POMDPs. Now, a lot of work in dialogue, so these works are only snippets. You'll find the detailed related work in our paper as well. But a lot of work in dialogue POMDP has shown that if you use POMDPs for dialogue management for a conversational agent, it's proved to be very effective. But most of them, they only take into account the language observation. They don't take into account both the language observations and the world observations of the human actions. And there is one work which is by Hui et al., which actually works on doing goal recognition while taking into account partial observability in both the world observations and the language observations, but they're limited to just one task. They can't extend it to multiple tasks. And one paper, which is going to be referenced throughout the rest of or my presentation as well, is the work Inside Plan Recognition by Wang et al., who actually has incorporated world observations for multiple concurrent tasks for humans. But again, they don't incorporate language feedback. So, what we want is we want to enable social robots to actually do goal recognition of the humans and can ask clarification questions when they're really ambiguous and get language feedbacks. So, we want a robotic dialogue manager which must keep track of the environment, the user state, and the dialogue histories internally if they want to assist in a successful task completion. And what we are proposing is to solve this problem is by combining expressive hierarchical task representation of hierarchical task networks, which are used by the Wang et al. Plan recognition model, and combine it with the sequential decision-making capabilities of partially observable decision process POMDPs. So we are introducing a novel model, which is known as dialogue goal recognition or the DAGR POMDP. So now this is actually particularly hard because of a couple of reasons. One is because the modeling of problems and the notion of solving the domains, that is for generating the optimal policy for the robot, is quite different in both the approaches. And hierarchical task networks, the way you decide that what's an optimal action for the robot is based on the knowledge base, while in case of, and they don't take into account anything related to utilities, while in POMDPs you're trying to maximize utility but you not necessarily make use of knowledge graph representations. So, and there's another problem, is that if we do have a dagger POMDP, here I'm showing you an influence diagram and I'm going to go over the high level overview of it, but you can see that it will have a large language observation space because it's incorporating all these language feedbacks, and it's going to have a large world observation for the human action as well. So how do we actually solve it? We actually take advantage of the hierarchical task representation presented by the hierarchical task networks. In particular, what we are trying to do is that as a part of the hidden state variables of our POMDP framework, we are trying to actually represent the human mental state, which is MT at any given time t. And MT is actually composed of further two state variables, which one is the human goal the high level tasks or goal that the human is trying to do, which we represent as G, and the lowest primitive action that the human is trying to do, which we represent as alpha. So say that the goal that the human is trying to do is wash hands, and the lowest primitive action for that is turn faucet. And we are trying to maintain a probability distribution of both of these. And we say that this is known as the human mental state. Now, in our case, we represent this human mental state as a hierarchical task network because we are assuming that the person is actually a planner with goals and sub goals that can be described hierarchically. And this is something which is also represented in Wang et al.'s work, where they're using HTNs to represent the human mental state as an HTN. Um, so further, actually going back to it, so we have large language observation, which is going to be the language feedback. We have world observations. In our case, we actually limit it as binary world observations about the environment state and about the attributes of the human. For example, faucet turn on, or hand is dry. And further, we represent W as the world state representation, and Q is the question that the robot has asked. So we represent the dialogue state, we represent the world state, and we represent a human mental state in order to have this belief distribution over the human's progress as the human completes a task. The action in our case, we have limited it to only language or speech actions. So in this case, the robot can either wait or can strategically ask a clarification question. Um, so for the belief update, we actually make certain independence assumptions and have been able to factor out this large belief update into world observation model and the language observation model. In the interest of time, I'm not going to go into detail of the equation, but I'm more than happy to discuss the factorization that we do offline. Um, Now, using this combined representation where we have HTN, where we are trying to use it to represent the human mental state, and a POMDP, where we are trying to see trying to infer the human's progress and decide and make the robot decide when to ask a question. Using this combined representation, we can allow the robot to commute an optimal dialogue policy, enabling it to reason about when to ask a clarification question and what specific question to ask. And further, as a part of this Dagger POMDP framework, we can also perform plan recognition of the human based on the human actions as estimated from the noisy sensor, as well as the language feedback. So what we do is we evaluate the performance of our Dagger POMDP over various cooking tasks. And we do it in a simulated environment, and we compare it with two baselines. We compare it with the always ask baseline and with the HTN baseline. HTN baseline only incorporates world observations. Always ask incorporates world observation, but always asks a question, while Dagger POMDP infers when to ask a question. The two metrics that we compare are the number of questions asked and the accuracy performance. And what we are trying to show is that in our case, and we do it in two scenarios: multiple goal wrong steps, where the human does multiple goals but can do wrong steps, and also when it can do wrong correct steps. And what we are trying to show is that in case ignore the side titles, those are a little incorrect, but you can see over here in the accuracy performance, in both of our cases, our blue line is better than the baseline, which is HTN without the language feedback, and it is very close to the orange line, which is always asking the feedback. So we are as accurate to the always ask baseline, and we are able to do that if we look at the left column, where we are asking way less number of questions as compared to the always ask baseline. So by incorporating language feedback and the world state information, Dagger POMDP, it achieves a 93.2% accuracy of goal and step recognition, and it can do so by asking only 34% more questions than no language feedback. The always asking is able to ask the correct question, and it only outperforms our policy by 1.7%. I do have an robot observation, but I can go over it in the offline questions. But we show that if the human does anything wrong, our agent is able to infer that the human is doing a wrong step and ask the clarification question at that point. Yes, I'll actually move to the next slide. So in conclusion, we present a novel algorithm for robots which can accurately encapsulate the human's mental state and progress during an ongoing set of tasks while strategically asking better questions in simulation. We combine hierarchical task representation with POMDP sequential decision making. And this is just one step for the ability to allow for realistic interactions to happen between social robots and a human, allowing for natural collaborations to happen over tasks. And I'm more than happy to answer any questions over email as well. So, yeah.
Sounds good. Thank you very much. All right, so our next speaker, because we are running out of time, so go ahead and sit up. So we will have Maya, right? We have Maya presenting the work haptic wearables to enhance tele-robot mediated handshake. So Maya is coming from St. Louis University. So with that, I will hand over to you. Go for it.
Hello, everyone. I'm Maya Zimmerman. Today I'm presenting on haptic wearables to enhance tele-robot mediated handshaking. Okay, so telepresence robots or telerobots kind of arose out of a need to for people that have embodiment and have presence and decision in remote settings. And kind of in the context of telerobots, you usually have two agents that are interacting remotely through a robot. So one of them is the co-located user or the user in the same local environment as the telerobot, and then you have the pilot user who is controlling that telerobot. Previous research has really demonstrated that platforms are often viewed as just Zoom on wheels, for lack of a better term. And that's mostly because they suffer from a way to allow you to realistically have a fulfilling, experience in that remote environment. So what our group hypothesized is that this lack of social connection is really due to an inability to kind of produce and experience tangible interactions, as well as gestures. So these critical components are often left out. Our previous work has demonstrated that the addition of a manipulator, kind of like the arm that we show here, onto an existing telerobotic platform has really enhanced its ability to produce social connection as well as social presence. So this mainly only occurs for the local user, the user who is physically present. For the controller, not so much. And really that is because you don't have those haptic connections that the local user kind of gets innately by being able to touch the robotic arm. And so this project really investigates the role of haptics for the pilot user and seeing how we can enrich that experience so that we can improve the telerobot as a whole. And so we did this through the process of handshaking. And we studied handshaking because it's one of the first kind of touch interactions that happens whenever you have communication that has various social meanings. We kind of use it to get a first sense about other people we meet, and it's prolonged and very complex to do. So it provides a lot of great questions for us to answer. And there's been previous work done on exploring remote handshaking through telerobotics. And this has been done through mostly grounded kinesthetic devices, but they're a little bit cumbersome for telerobotic manipulation because you're already trying to have cognitive effort and use a lot of space trying to control it. So having a grounded device usually doesn't work out well for the process. There has been some other work that's been focused around wearable devices, but not much has really been explored within that space. So wearable devices have been explored, and using haptics within wearable devices has been explored not to the largest extent, but to a decent extent. So we have devices that work for wrist squeezing or mostly other forms of communication. And so these prior works really led to our research questions, which are: do haptics improve social presence and remote handshaking for the pilot user? And if so, is a direct analog human-to-human handshaking actually required in order to create that improved social presence? So what we did is we created two gloves, one that does radial squeeze and one that does vibration, in order to kind of see and have an initial sense of its section force. So the radial squeeze glove uses a servo motor as well as a spool attachment to compress a spool, or compress the elastic band that's attached to the spool. And the vibration glove uses coin motors that are ERMs at 4 different points on the hand in order to create those vibrations. And these gloves only do on-off actuation in order to keep it as simple as possible and not have any discrepancies with having patterns or anything like that. This actuation is controlled by an Untitled Plus microcontroller on the top of the gloves. So what we did is we used these two gloves along with a glove that didn't have any actuation components on it, which uses a control in order to run an experiment. So what we did is we had each participant do 3 haptic interaction sets, and each of these sets really included 4 handshakes. So you were introduced to 2 Confederate panelists remotely, and they would then introduce themselves, take your hand. After that, they would ask you a couple of questions just to kind of get to know you a little bit better, and then they would say, okay, conversation's over, nice to meet you, and shake your hand again. You get 4 handshakes throughout that experience, and you do that once for each glove type. This audio visuals were all communicated over Zoom, and the panelists control the actuation through a push button that the participants couldn't see. And so in order to query users about how they felt during these interactions, we had 2 questionnaires. So after each interaction set, they answered 7 questions, which covered these topics here about their level of engagement or interaction for the most part during the experience. And then after the study, in order to get a better global sense of how they felt about it, we had them rank each of the 3 feedback types from their favorite to least favorite, and then give us some general open-ended ideas through the last 2 questions. And so we ran this preliminary study with 10 participants. We found that there was significant difference between the squeeze and no haptic and vibration and no haptic in 2 out of the 7 categories. And those were feedback, satisfaction, and social connectedness. And this was further corroborated by the fact that the majority of participants rated squeeze as their favorite of the interaction types and vibration second. None of them considered the no haptic condition as their favorite. So these initial findings really suggest that haptic feedback, and specifically vibration and squeeze, do have the potential to improve feelings of social presence in remote handshaking. And that a direct analog may not necessarily be required in order to promote those feelings of social presence. That being said, there's a lot of work that still has to be done in order to explore the extent of how much this rings true. But there's also some other things that we'd like to do in the future as well, such as explore other feedback modalities like thermal or normal force feedback, or shear. We want to also see it increase feedback complexity, so things like haptic patterns or combining different modalities can really affect how social connectedness plays into haptics. And even though this study primarily talks about handshaking, we'd like to see that also this among other types of social contact interactions like high fives or hand holding or you name it. And that is all I have. Thank you guys for listening. And now I know people on the screen. Thank you.
We might have to get us back on track. So I don't want to send people in coffee, but I think they are very keen talks. So we can take 1 or 2 questions if there's any from the audience. Go for it.
I have a question for Ifra about the sort of long-term task planning. I'm curious, it looks like you're getting information from the current actions of the user and the sort of explicit speech queries. And how good is that for sort of long-term prediction of not just the current task, but like several steps down the line? sort of long-term predictive horizon?
So right now we have tested it only the current. Thank you for the question. It's a really nice question. So right now we've only tested it on it's doing it at the current step, but we do run Monte Carlo tree search for long time horizons sequences. So it does take that into account. But right now the predictions are just happening for the current step, but they do take into account run sequences for the long term horizon. And we do it like for I think it's like 20 steps down the road. We run the sequences for that and take that into account for the current steps prediction. Does that answer your question, or were you asking something differently?
Thanks.
Maya. So one of your research questions was like, is a direct analog required for the distance statement? So if you're adding like normal force and maybe thermal, it feels like you're going to like analog, or is it going minimum volume?
So those examples that I kind of gave at the end were just ones that I thought of. It's kind of easier to draw direct analog, especially with like experiences that you feel tactily yourself, right? So you think about the warmth of somebody's hand or the actual like normal force that you feel as well. But there are other things you can do. I mean, of course, there's rocker mechanisms, all sorts of other haptic feedback as well. Those are just examples I had, off the top of my head and things that I'm currently working on. Those don't necessarily mean that we are strictly delegated to those. Those are just the ones that I kind of have coming down the pipeline.
Yes, I have a question for Juan about his proximity sensors or sensing proximity as well as sensing tactile. And you were saying that you changed the opacity of the surface, the sense if something is nearby. Is that affected with the lighting conditions in the area that you're in, and how accurate are your measurements of how close someone is? He's muted. Oh, I think you're muted.
Sorry. Yes, you can hear me?
Yeah.
Thank you very for your question. Actually, I didn't show much the results, the characteristic results of the distance of the proximity sensing, but actually there is a reliable range that the sensing can give us. It's around 2 to 10 centimeters, but below 2 centimeters and above 10 centimeters, it gives very noise results. But I think the problem is not lies in the hardware, because it uses cameras, and the camera views can attain quite far than the reliable range. But it lies in the software, I think, because we are using monocular depth neural network to reconstruct the map. But we only use the pre-trained model, but we don't have much fine-tune on that model, so it gives relatively bad results on the accuracies. So it's but I think the preliminary results is promising.
Thank you. Sounds good. So in the interest of time, let's thank our speakers again.